So I'm just going to follow what Karthik asked me to do, to give you some brief about parameterized interactability, not parameterized tractability. So I do have absolutely 0 slides on parameterized tractability. So how many of you have heard parameterized complexity or parameterized algorithms? Okay. So at least I don't have to define the notions and everything, and I can directly go into some of the history behind or the notions behind parameterized interactivity, how it started, because generally we somehow gloss over it, but there are some interesting questions and history behind it which could be useful to tell you stories. Okay, so you might have seen lots of some positive results in parameterized algorithms, but what kind of negative results do we have? Like, for example, so the click that Subhas defined is also hard in the world of parameterized complexity. And what it means that it is hard, that we do not expect to have an algorithm with running time f of the size of the click that we desire, and the input dependence is still purely polynomial, okay? Or can be so that the problem like vertex cover, for which is like, so you have an edge, one of the endpoint must go into the solution, so you can recursively try to solve a problem by either trying to take this vertex, solve a smaller problem, take the other vertex of the edge, and that will give you 2 to the power k algorithm. Can you do better? Okay? And so this would require showing that, P is not equal to NP, and if P equal to NP, then example k click is anyway polynomial time solvable, right? So can we give evidence for some such negative results? So that's the kind of things we will talk about in this lecture. So goal of this talk are like 2 goals. Explain this theory behind some interactivity results in parameterized interactability, like W1, Mini1, ETH, and to take you towards the other talks that is going to follow, which will use a lot of ETH, Seth, and all this for doing other kind of interactivity results in polynomial time. So just take you there, and give you some examples of parameterized reductions which closes connections between these objects. So here's a classical complexity. So first let me define non-deterministic Turing machine. So what is non-deterministic Turing machine? It's a single tape, finite alphabet, finite state, head can move left and right, only one cell in a time, but in each step, the machine can branch into many states, right? So like a deterministic, where it can only go to one state, in non-deterministic Turing machine, you should think of this as like a branching tree. At any state, it can branch into many ways. And run is successful if at least one of the branch is successful. And what is NP? It's like the class of all these languages that can be recognized by a polynomial time non-deterministic Turing machine. And what is polynomial time reduction? So polynomial time reduction from a problem P to problem Q is a function with the following property, right? So it maps an instance of one problem to an instance of other problem, such that yes instance goes to an yes instance, and no instance goes to a no instance, right? So unlike the reductions which Subhas was making, where yes instance was going to yes, but a no instance was still going to no, but much worse no, but here we are happy with no just goes to normal no, okay? So this is what the old classic way of showing something is NP hard, is that you take your favorite problem, and you want to show that it is NP hard, then you say, hey, look, I started with a problem which is already known, and if I can give a reduction to problem which I want to show hardness, right? So if it had a good algorithm, then my old problem for which I know a lower bound will have a good algorithm. So that's the old thing. So the reason why I told you is that this is a template which we are going to follow for different models during this talk, with different fine-tuning of what necessity of how this file looks like, how does this yes goes, where no goes. These are the kind of things that we will take care during the talk. Okay? So this is the classical complexity. Now let me give you a little bit about W1 hardness. So to build a complexity theory for parameterized problems, we need 2 concepts: an important notion of reduction and an appropriate hypothesis, right? So the way you have a classical world has a hypothesis is P and P. We also need a hypothesis in this world. So what is the proper notion of hypothesis, and what kind of reductions do we need so that we can show if one problem is hard in this world, then the other problem is hard in this world, okay? And polynomial time reductions are not good for our purposes. So example, let me show to you. The graph G has an independent set of size k, if and only if it has a vertex cover of size n minus k. In the world we are going to talk about, vertex cover is easy. It is FPT. Independent set is hard. So this reduction does not distinguish that vertex cover is easy and independent set is hard, right? In the classical world, all we care about whether it is in polynomial time solvable or not, then this old reduction was okay. But in this world, this is not okay. Okay? So we need to have a reduction which somehow taps into this notion of parameter in some sense. Okay? So first let me define what parameterized reductions are. So what did we define a problem in world of P versus NP? So this is a reduction which took polynomial time. So now I allow myself to take FPT time because ultimately my goal is to solve the problem in FPT time. So if it takes FPT times, it just adds an FPT time to the whole running time. Okay, so that's perfectly fine. Okay, and as always, yes instance goes to an yes instance, no instance goes to no instance, but the two things which are changed, one is the running time that algorithm is allowed to take, or the reduction is allowed to take, is FPT, but more importantly, the parameter of our interest is not allowed to grow as a function of the input size. It can only grow as a function of the parameter we are interested in. So that's the red color bullet. Yes?
Can function G be any function?
For the purposes of this talk, we will fix ourselves with a computable function, which basically means there's a non-deterministic Turing machine or deterministic Turing machine which can compute this. So now, the way in the old world, what did we imply P versus NP world? So if there's a parameterized reduction from problem P to Q, and Q is FPT, then P is also FPT. And other way around, how will you show? If P was not FPT, and you have such a reduction, then it implies that Q is not FPT. So this is the reduction we will always be making. So now notice the fact that in this world, we care that the K is only growing as a function of K itself. Okay? So for example, look at the non-example, right? So if you transform independent set into a vertex cover, K goes to n minus K, it's not an example. But if you transform an independent set by taking the complement graph, then K, then this is a very proper reduction to the clique, because independent set will turn into a clique. So this is a proper reduction in the world of FPT, because time taken is polynomial, which is still FPT, and K goes to K. So this reduction is an allowed reduction in this world. The first reduction is not allowed reduction in this world. Okay? So if you have any question, please ask. Yes?
Why that is not allowed, non-example on each constraint is violated?
The K. K goes to n minus K. And this n minus K, it is not necessary that for every instance you will be able to bound as a function of K itself. Okay. So a useful variant of clique which occurs in parameterized complexity quite a lot is called multicolor clique, okay, or a partition clique. So what is there? So the vertices of graph G are colored with K colors, and you wish to find a clique which consists of a vertex each from each color. So this is why it's called partition clique or multicolor clique. And now I'm going to give you a reduction, parameterized reduction from clique to a multicolor clique. So here's an instance of a parameterized multicolor clique. So V1 you can think of as color class 1, V2 as a color class 2, and dot, dot, dot. And from each color class, you need to pick a vertex. So how do you make this reduction? You basically replace G, so like by K vertices each for each color class. Like you replace every vertex V with K vertices, one in each color class. Okay? And if U and V are adjacent in the original graph, then you just make all the copies adjacent to each other. So that's it. So what we did, we took the G, we took K copies of it, thinking of each copy of the graph as a color class and different. And how do we put an adjacency? If two vertices were adjacent, then you just put the edge between them. Okay? Now you can, not very hard to show that if you have a K clique in G, then you have multicolor K clique in G prime, because you take those K vertices, go into different color classes, and that will form a clique. So the forward direction is fine. In the reverse direction, if you start with a multicolor clique, the way we have put adjacencies, you can show that they're going to form a clique. Okay? I mean, maybe there's some subtleties here and there, but there's not too much here, okay? Okay, so you can similarly reduce to multicolored independent set. Okay? Now, I'm going to give you a reduction, which in my opinion is a very foundational reduction in parameterized complexity. It's a reduction from multicolored independent set to dominating set. Okay? So what is a dominating set? So you can think of a dominating set as a smaller version of set cover. So you're given a graph G, and you're asking yourself, does there exist k vertices whose, if you look at all the neighborhood of that, then that's a whole vertex set. Or in other words, for every vertex, either you belong to that dominating set or one of your neighbors belong to it. Okay? So now I want to give a reduction from multicolored independent sets. What is a multicolored independent set? You're given k colors, k coloring of a vertex set, and you are looking for an independent set that consists of a vertex each from each color class. Okay? So now how do I give such a reduction? So G already has color class V1 to Vk. We construct a graph H such that G has a multicolored k clique if and only if H has a dominating set of size k. So how do we do that? Is that first look at each part, just turn into a clique. Right? And then you put some guard vertex x1, y1, which is private to these guys. Now, if my budget is k, from each k clique, you have to pick one vertex edge. So k dominating set has to contain one vertex from each of the k cliques, v1 to vk, to dominate every xia, ya. So up until now, there's nothing. Now we are just going to add a small gadget, which will take care of adjacencies. So how do I take care of that? So for every edge, you have a vertex, we. Now you know that it's an edge between two colored classes, right? So you make him adjacent to every vertex in that color class except the incident his, and you make him adjacent to every other vertex in the other color class except the vertex it is adjacent to. Now what does that ensure? Now in the reverse direction, if you're going to pick up a dominating set, look at the two vertex from the two different color classes, right? Can they have an edge between them? Because if you have edge between them, then look at the we, right? He is adjacent to everybody else except this vertex, and he is adjacent to to not that particular vertex, but everybody else. So WU cannot be dominated by anybody. So now I have shown to you a reduction from multicolored independent set to dominating set. Okay? So we'll keep this in mind, that there's a reduction from multicolored independent set to dominating set. Now you can come up with a variance of dominating set like, okay, red-blue dominating set or set cover, hitting set. All these problems are equivalent under parameterized reduction, hence they're at least as hard as clique, right? So we started to build our world starting from the clique. Then we showed it is multicolored clique, and same by some complementation trick, you can show multicolored independent set is hard. Then we gave a reduction to dominating set, and you can give a reduction to all kind of variants of dominating set. So now we have started to build small world, starting from the reduction from clique to all these problems. So here's a basic hypothesis, okay? It seems that parameterized complexity theory cannot be built on assuming P not equal to NP, so we have to assume something stronger. So let's choose one basic hypothesis. It's like we call engineer's hypothesis. K clique cannot be solved in f of k n to the power big of 1. You might not like to believe it. So let me add some theorist hypothesis, and this is why I took the non-deterministic Turing machine in the beginning, is that k step halting problem. So now we make a version of halting problem for parameterized complexity, which says, given a non-deterministic Turing machine, is there a path that on the input you will stop in k steps, right? And what we can, this we will assume that cannot be solved in FPT time, right? So this looks like, oh, we're talking about some non-deterministic Turing machine, some halting problem. So this looks more plausible or believable than believing that k clique cannot be solved in f of k poly time. Or the last hypothesis that I will talk a little bit towards the end is ETS, that n variable 3 sat cannot be solved in sub-exponential time. Okay? Which hypothesis is more plausible? So what we are going to show that engineer's hypothesis and theorist hypothesis are actually same. And we are going to give a reduction from ETH to theorist hypothesis in the talk. Okay? So, I mean, I had slides to give you this reduction, but it looked too much of bookkeeping, so I decided to not, and just tell you one side. So how will you give a reduction from independent set to k-step halting problem? So you take a graph G, integer k, you construct a Turing machine M, and your integer k prime will be like roughly order k square, so that M halts in k prime steps if and only if G has an independent set of size k. So what will be your alphabet? All the vertices of G. So in the first step, what does Turing machine does? It just goes and write down the non-deterministically cells. It just goes and write down the k vertices of independent set. Now all you care about is to check whether they do indeed they form is an independent set. So for some I between 1 to k, you move the ith cell, and now you go and just check whether there is an edge or not. If there is an edge, then you just loop forever. And if M does k checks, and each check can be just done in some 2k steps, so your algorithm will stop, your Turing machine will stop in some order k square steps. Right? So this is the way you can reduce independent set to Turing machines. But there's just not very hard also reduction from Turing machine to independent set. And how do you do it is, I'm not going to tell you this, is that look at, it's only k step. So the Turing machine cannot read beyond some first k plus 1 steps, k plus 1 cells. Now you can encode this phenomena as like some k plus 1 square click, and how you put an edge between these clicks, telling, oh, at this cell, at this, what happened, and some inconsistencies, and you can do it. So it's just about bookkeeping, but you can come up with a reduction from this. Okay? So for the purposes of this talk, I will not talk about it. Okay, so what's the summary? Summary is that independent set and k-step halting problems can be reduced to each other. That's engineer's hypothesis and theorist hypothesis are equivalent. And independent set and k-step halting problem can be reduced to dominating set. So we have seen these two things. Yes?
What is the exact way of making hypothesis? They just think for a couple of years, then they see they cannot prove something, they say, okay, it is hypothesis.
Yes, in some sense. Or more than that, I think there's another way is that how general your problem is that it can encode many, many more questions. So hoping that that will be central to difficulty is much easier to believe than anything else, right? So I'll come to that moment. What do these things mean in a minute, and why people hypothesize the way they do. For example, SAT. Why do you think people always talk about the tractability of SAT or circuit SAT? Why? Because it has the power to code many, many more things than a normal, say, vertex cover, for example, right? So hypotheses are generally done on a problems which is, we believe, is central to hardness of many other things. I hope I have answered a little bit. Okay? So now the question is there a reduction from dominating set to independent set? Right? Is there a parameterized reduction from dominating set to independent set? Probably not. So unlike in NP completeness, where most problems are equivalent, in parameterized complexity world, we have hierarchy of problems. So independent set is known to be W1 complete. Dominating set is known to be W2 complete. I mean, it doesn't matter if you don't care about whether the problem is FPT or not, whether it is W1 hard or W2 hard or W3 hard, it absolutely doesn't matter, right? But if you're thinking from the complexity perspective, just as a curiosity, is that can you give a reduction from dominating set to independent set, like FPT reduction? Is it possible at all? I mean, forget about anything else. At least I find that a very curious question, and finding an answer to this curiosity helps you do many more things at a time. So now let me tell you what is W1, W2 that people hear, what they are, and from where do they come, right? So they are basically coming from the circuits. And now we'll talk a little bit about circuits. So here's a Boolean circuit. So what is a Boolean circuit? You can think of this as a DAG. It has some bunch of inputs, some AND gates, some OR gates, and at the end, there's a root gate, which basically is, so you set these variables to 0, 1, because we are only talking about Boolean circuit. And at the end, whether this circuit evaluates to 1 or not, based on the gates in between, okay? So what is the circuit satisfiability given a Boolean circuit C? Decide if there's an assignment on the inputs of C, making the output to be true. So that's basically circuit set. So what is the weight of an assignment? So in parameterized complexity, we need some parameter. So of course, there are some obvious parameters. One obvious parameter is size of the circuit. But the other parameter that we use is weight of an assignment. And what is the weight of an assignment is the number of variables that you set it to 1. So it's like k. Right? Do you have an assignment of weight k? Okay? So let's see if we can reduce independent set to weighted circuit satisfiability. Okay? So now what we have on the top, x1, so think of these as a vertices, right? And what do you want? You want k vertices that form an independent set to be set it to 1. How do I do this? So then I have a negation. All I care is that between those two vertices, there is no edge, right? So I want to, how do I want to think about it? I say, hey, if I both set them to be 0, if I set both of them to be, what do you call, 1, right? Then that shouldn't be true, because then there's an edge between them, right? So how do I encode this for every edge? Say, for example, if x1 and x3 had an edge, then by negation, I have put a OR between them, right? So you will see the second level OR. It is for every pair of vertices which have an edge, I have OR between them with a negation. What does that mean? This is set to true only if one of them is set to 0, right? So if you set k variables to be 1, right, then if they had an edge, then the corresponding OR that evaluates them will never be set to 1, which means this formula, this circuit will never be satisfied to or set to true, right? Which implies that now I have reduced k independent set to weighted circuit SAT of this circuit. Okay. For dominating set, if you notice, this is like x, again, I have like gates corresponding to, like input gates corresponding to vertices of my graph. And what you see this OR is basically OR of neighborhood of that. So if x1, x2, x3, x4, x5 have a neighbors, then you have an OR of all of this, which basically means that if you're looking for a dominating set, then for every closed neighborhood of a vertex, you should pick at least one vertex, right? So that is what is done in this circuit. So if you have a dominating set of size k, then you just set those k variables to 1, right? Then automatically for every neighborhood, intersection is 1, right? So the corresponding OR will be set to 1, and then you have this big N, okay? So I have reduced both independent set and dominating set to an instance of circuit set, okay? Now I'm going to show you the differences between these two circuits, okay? So it looks like to express dominating set, we are needing much more complicated circuits, right? So what do we mean by complicated circuit? Both of them looks like depth 2, simple, we just described it, but there is a catch, what is called weft and depth of a circuit. So what is the depth of a circuit? It's a longest path from the output gate to any input gate. So that's the depth of a circuit. And what is the weft of a circuit? You look at a gate is called, like big gate or large gate if it has more than 2 inputs, okay? How many number of large output gate is there starting from an output gate to input gate? So if you look at independent set, the only large gate is this, because this is 2, 2, 2. This is the only gate which has more than 2 inputs. So from any leaf to root path, you have only one big gate. So this is why weft is 1, depth is 3. But look at dominating set. Now this OR gate depends on whether it is 2 or 3 or 4 or 5, depending on what is the size of the closed neighborhood is, correct? So even these can be big gate, and this big OR of them can also, big AND of all of them can also be big gate. So in this circuit, weft is 2, depth is 2, correct? So there's a basic difference between these two circuits is, in one, depth is large, but weft is 1. In the other, depth is small, but weft is large. And this weft, how many weft you have determines this 1, 2, 3, 4, 5 that you see in W1, W2, okay? So more formally, so let CTD be the set of all circuits of having weft at most T and depth at most D, okay? So a parameterized problem is said to be in the class WT if there's a constant D and a parameterized reduction from P to weighted circuit satisfiability of CTD, meaning depth of this circuit is at most T and depth is D. Okay? So now we have seen that independent set is in W1 and dominating set is in W2. And the fact is independent set is W1 complete and dominating set is W2 complete. Okay? So that is where this you see W1 and W2 and these things, they come from these circuits. Okay? Any question? Okay? And we believe that this hierarchy of W1, W2, we don't know whether they're equal, but we believe that these hierarchies are W1 is properly contained inside W2, which is properly contained inside W3, so on and so forth, right? And now if you see if someone writes WP, it means number of big gates are like as many as polynomially, right? So that's all that it means. Okay? So if any W1 complete problem is FPT, then FPT equal to W1, and every problem in W1 is FPT. Similarly, if any W2 complete problem is in W1, then W1 equal to W2. So if there is a parameterized reduction from dominating set to independent set, then W1 equal to W2, which we still don't know in last 3 decades. Yes?
Are there any natural W3 complete problems?
Some variants of circuits are, but there are, at least for W3, there are some natural graph problems that people made some point of time, but I don't remember them.
Okay.
Like, they're not natural.
Okay.
If people have to write a paper to make a problem, then I personally don't find it very natural, but that's very subjective definition. Okay, so from where does the word weft come? So it basically comes from, it's a term related to weaving cloth. Okay, so this wrap around of weft is what we call, it is a thread that runs from side to side in the fabric. Okay, so this is what is called weft. So I think this is from where people have got this word weft. Okay, so just to tell you from where does this word, I just Googled it and it looked interesting. Okay, so let me give you one slide on parameterized reduction before I move to other objects of this talk, is that, so typical NP hardness proof, reduction from click or 3-sat, representing each vertex edge variable clause with a gadget, usually does not work for parameterized reduction because we cannot afford to increase parameter in every gadget. So you have to be slightly smarter when you do this. Okay? So types of parameterized reduction, it tries to keep the structure of the graph. It tries to have some sort of vertex representation. There's also a notion of edge representation and this, but I will not tell you anything because that's not what I plan to tell you today. So I want to move to, so I have told you a little bit about how W1 comes. Now I want to tell you another foundation that parameterized complexity people tried to do. Okay? So this is called mini-1, or towards quantitative lower bounds. So notice what happened in last decade or so. You go to any conference, you see this problem cannot have n to the power 2 point blah blah algorithm unless some APSP conjecture fails or 3-sum fail, right? So what are these kind of lower bounds? These are concrete running time lower bounds. We can achieve this running time, we cannot achieve this running time. What I have been telling you up until now is all about whether you belong to this class or you don't belong to this class. Similarly, the P versus NP can only tell you whether you belong to this class or you belong to this class. But it cannot tell you anything about the form of running time that you're able to rule out, right? So to able to rule out any form of running time, we need something more, and that something more is what I'm going to spend my next 30 minutes telling you about. Okay, so we already know that W1 hard problems are different than ones which are FPT. Now, however, within the FPT, we have different dependency on the parameters. Some are sub-exponential, some are single exponential, some are k log k, some are even double exponential, some we don't even know, especially those algorithms coming from graph miners, how many towers of 2s are there, right? So there are variety of algorithms with variety of running times. Like similarly for W1 hard problem, Some problems are f of k n to the power big O of k, some are like root k, or some are like log k. I mean, you name it. So it seems that there are some hierarchies of subclasses corresponding to different classes of running times. The way in the polynomial time world now that we have made, like something like k sum, 3 sum, n square, n cube, APSP, they are just defining that these problems have these kind of running times. So they are defining a class of problems in itself. So similarly, it's very natural for people 2 decades back is that now that they have shown lots of FPT and W1 hard, they were wondering is that the form of running time that they have is the correct one, or something better can be done, or somehow we can come and do tightness. So Karthik also asked me to tell him some important problems that people will care about in FPT in terms of approximation. I don't have those slides today, but I will tell them tomorrow, which I still believe are interesting and somehow maybe doable, but we might need help from people who know hardness of approximation much better to come up with right maybe conjecture or hypothesis to name them. Okay? So what will be like to separate this class? We need some methodology for proving lower bounds. So ideally, what you like to show that f of k n to the power big of 1 is possible, little of f of k is not possible. So dream will be like 2 to the power f of k is possible, 2 to the power 1 minus epsilon f of k lower bound. So like tight lower bound for every kind of thing. So p equal to not equal to np, or even fpt not equal to w1 is probably not strong enough to serve as a source of hardness for these kind of fine-grained complexity classifications. Okay? But if we are pessimistic enough, sometimes dreams comes true. So people are pessimistic enough that their dream come true. And here are, so before I go, let me tell you what do I mean by little o, because this is very confusing if you like, so mathematically this is what it means. What I will mean little o all the time is in parameterized complexity, sometimes we call it O effective. So given 2 function from natural number to natural number, I'm going to say that f is O effective of z, or big O, little o of z, if there exists some n0 in n, and some function h, which is non-decreasing and unbounded, such that for all n greater than or equal to n0, f of n can be upper bounded by g of n divided by h of n. Right? So, so that we don't have a confusion when we go forward, I thought that I will put up a slide what I mean by little o in this talk. Okay? Okay? So it's like the running f of n is upper bounded by g of n divided by some function which grows as n grows. And that's a way to keep it in the head. Okay? So here's exercise. So that the following functions are FPT, 2 to the power little of k log n. I think this I will do it anyway in the talk, and log n to the power k. It's a good exercise. Given this definition, that these are FPT. What I mean by FPT, that you can show 2 to the power little of k log n is upper bounded by some g of k times n to the power big of 1. Okay? And that is an important thing that we will keep on using starting from this. So let's go back to circuit SAT, because that is where we all started. Okay? So what is circuit SAT? Again, you are given a Boolean circuit of size S. Decide if there's an assignment on the inputs of C making the output true. And now I have used the word size S. So let me clarify what I mean by size S. It's a total number of gates and input lines, wires in the circuit C. So that if you think of circuit as a DAG, then it is basically number of vertices plus number of edges. So this is what I mean by size, not number of inputs. It is important that I distinguish between number of input and the size of the circuits. So, and what is a circuit SAT hypothesis? So here's a circuit SAT hypothesis. There is no algorithm with running time 2 to the power little o of S, where S is a size that determines for Boolean circuit C of total size H whether it is satisfiable or not. So of course there's a 2 to the power S algorithm. You try all possible assignments on the inputs. Since S also includes the number of inputs, 2 to the power number of inputs is less than or equal to 2 to the power of S. But I'm asking, can you do better than this trivial algorithm? And let me say for a moment that we cannot. And that's a circuit SAT hypothesis. Okay? So this was an attempt by people in parameterized complexity to start having a running time bound lower bounds. And I will tell you how. And this might sound in vague, but later I will connect to all the things that we know now. Okay? So, but it's important that we use, for the first time, a Hessian hypothesis where we are talking about the running time. Up until now, we cannot decide in this time, but now we are talking about a specific form of running time. Okay. So now comes the kicker. Okay? Something called mini circuit SAT. Okay? So what does mini circuit SAT consist of? Positive integers k and n written in unary. It's like what it means. So basically it means this input, you make it big just by padding. You write k, 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 1, k times, then you write n times. It means nothing, but you just write it down. It's just a padding. And you're given a Boolean circuit C of total size k log n, and parameter is k, the natural number. Decide if there's an assignment on the inputs of C, making the output true, right? So this is what I call mini circuit SAT. Why? Because it's not too big. You have made it big just by adding this bogus ones by padding. And that is important, as you see now. So what is the size of the input here? So the size of input is actually n plus k log n, right? N that I have written in unary, and the size of the circuit. So what is the trivial algorithm? So 2 to the power k log n, kn to the power big of 1. This we can do. And now, because what is 2 to the power big of k log n? It is n to the power big of k. So it's an XP algorithm in the world of parameterized complexity, because n is written as unary. If you did not write this, then you cannot say 2 to the power big of k log n as an input is n to the power big of k. So this is a trick that we used. Okay? Anything non-trivial? So all I'm asking is that for this problem, mini circuit SAT, can we get anything who is 2 to the power little of k log n? Okay? So equivalently, is mini circuit SAT is FPT parameterized by k? Right. And that's our first theorem. Mini circuit SAT is FPT if and only if circuit SAT hypothesis fails. So now we have started to get some sort of running time analog for this. But still, we are still talking about that mini circuit SAT has no FPT algorithm parameterized by k. So let's see how the proof goes. So suppose this is where I'm going to use that 2 to the power little of k log n is FPT. Okay? So suppose mini circuit SAT is solvable in FP time f of k n to the power c. So what will you set k equal to? You set f inverse of s. That's my k. So, and what do I set n? Because now I'm giving what I'm trying to give. I'm trying to create an algorithm. So given an instance of circuit SAT, I'm trying to create an instance for mini circuit SAT so that I can use the fast algorithm for mini circuit SAT to solve my circuit SAT problem. So now I have a what do you call, flexibility to choose what my k is, right? So I choose my k equal to f inverse of s, and n equal to 2 to the power s by k. So then what is s now? K log n, just by setting up this. For example, if f of k was like 2 power k, then what will I set k equal to? Log s. Okay? So we can assume that k equal to some slow growing function of s. Okay? So now c times s by k plus log s is the little of s, because f is inverse s is a slow growing function of s. So now if you use the FPT algorithm, then what is the running time? F of f inverse of s, 2 to the power s of k, to the power c, and you do this sum, is 2 to the power little of s. All I was trying to do is it's just the rewriting of these terms and playing around with little o, circuit SAT hypothesis fails. So this is our first. This proof can be made to work for any problem. Mini x is FPT if and only if x has 2 to the power little o of size algorithm. This is very important. This will come to help us in a minute. Okay? So what is mini 1 or M1? Parameterized problems that are FPT reducible to mini circuit SAT. This is called mini 1. Okay? So if your parameterized problems that are FPT equivalent to mini circuit SAT are basically complete. So you can show that parameterized reduction from P to mini circuit SAT, parameterized reduction from mini circuit SAT to P, then you can show that this problem is complete for this class mini SAT. So let's talk about more miniaturized problems, like mini 3-sat. What is mini 3-sat? Your instance has size k log n, but you have written k and n in unary, and you're asking whether phi is satisfiable or not. Or mini vertex cover, right? Graph size is k log n, and you want to say whether there's a vertex cover size at most r or not. Mini independent set. I mean, you name it. So for every parameterized problem, I can define a mini version of that. And what did our theorem, previous theorem, prove? That any of these version is FPT if and only if you have 2 to the power little o of size algorithm for that problem. Okay? So you can show completeness via, if you look at a normal reduction from circuit SAT to 3-sat, they all are linear in the size, right? So this will imply that if you apply to this miniaturized, they all will apply, they will show you that there's a linear, these are like becomes an FPT reduction, and then you're perfectly fine, okay? So, okay? In fact, they are mini one complete because all these problems you can write it as a circuit SAT. So they are complete. But there's a kicker is that, but where is mini one in this hierarchy? So you can actually give a reduction, mini independent set parameterized by the size of the independent set is mini one hard under FPT Turing reduction. No, this is wrong. It should not have been mini, it should be independent set. Independent set parameterized by the size of the independent set is mini one hard. Means you can give a reduction, you can reduce a complete problem in the mini one class to independent set, which implies that every other problem reduces to independent set, which implies that FPT is contained inside mini one, which is contained inside W1. So this is just a digression. Okay? I'm not going to give you this reduction. This reduction is also, so there's wrong. Mini is not in the slide. It should be independent set parameterized by the size of the independent set is mini one hard. Okay, so let's look at some consequences. So what did we learn? 3-sat has 2 to the power little o of m plus n algorithm if and only if mini 3-sat is FPT, if and only if mini circuit SAT is FPT, and if and only if circuit SAT hypothesis blah blah has 2 to the power little of CS algorithm. So this is the first consequence. You can do this for the vertex cover, has 2 to the power little of m plus n algorithm blah blah blah. But for parameterized reduction, now I'm going to show to you that if vertex cover has 2 to the power little of k star algorithm, here k star is solution size, I'm not saying if and only if, then that implies mini vertex cover is FPT, right? And then blah blah happens. Okay? So that's our first non-trivial lower bound that we know there's 2 power k star algorithm, but I'm now saying to you that 2 to the power little of k star algorithm doesn't exist. Again, it's just bookkeeping. If vertex cover had 2 to the power little of k star algorithm, then mini vertex cover is FPT. How? So there exists H, so that what you can write 2 to the power little of k star as? You can write 2 to the power little of k star as, it's like some k star divided by some hk star function. So you run this algorithm with k star equal to k log n, that's what you will do. So this is running time. Now, 2 cases. Is k less than h log n? Well, if k is less than h log n, then this running time is n. Else k is more than h log n, then log n is less than h inverse of k. Everything is FPT. Done. So this bookkeeping is not that bad. So we got our first lower bound result that unless circuit SAT fails, mini or blah, you don't have 2 to the power little of k star algorithm. Okay. So vertex cover has no 2 to the power little k star algorithm unless FPT equal to mini 1. Right? So it's an exercise. Vertex cover has no 2 to the power little of n algorithm unless FPT equal to mini 1. Can you show that? Kernels. Okay? So you have to use 2k size vertex kernel, and that will help you. Okay? What it does not imply is that if circuit's hypothesis fails, then vertex cover has no 2 to the power little of n algorithm. This it does not imply. All it can say that it does not have 2 to the power little of n plus m algorithm. That's all that it says. Now, this is where the magic comes. We get to exponential time hypothesis, right? So what we know at this point of time? We know that for vertex cover does not have 2 to the power little of n plus m algorithm. if the circuit SAT fails. Okay? So what is exponential time hypothesis? I will tie them up in the end of the slides. That 3 SAT cannot be solved in the number of variables. Right? It's 2 to the power little o of n kind of assumption. So I'll give you what is the formal definition of ETH, sparsification lemma, ETH and some classical NP hardness reduction, ETH and W1 hard problems. Okay? Hopefully. So what is current known about SAT? So you can solve SAT by exhaustive search, like 2 power n variable, SAT, without assuming the number of variables in each clause. And QSAT has like 2 to the power gamma qn algorithm, where as q increases, the gamma q keeps on increasing. Okay? So what the current status exposes 2 barriers hard to break. One is, can we get 2 to the power little of n algorithm for SAT? 3 SAT, not SAT, 3 SAT. And can we get 2 minus epsilon to the power n algorithm for general SAT for some epsilon greater than or equal to 0? Right? So this was true 10 years, 15 years back. This is true even now. So what is the definition of ETH? For q greater than or equal to 3, let delta q be the infimum of the following set. So look at all the algorithms that can solve QSAT, right? 2 to the power c of c per. You take the infimum of all this c. So what does conjecture tells? So exponential time hypothesis tells us that delta 3 is strictly greater than 0. And strong exponential time hypothesis tells us as limit q tends to infinity, this delta q tends to 1. The reason I did not tell in the previous way, because that informality is okay for many reduction, but this is the right way if you want to do randomization, randomized version of ETH or randomized version of SET. So this is a much better way to tell. Okay. So what is plausibility? So ETH is generally considered as plausible. Many still believe that SET can be refuted any time. But SET-based reduction at least tells you something interesting, that hey, if you want to, SET is a central problem, if you give a reduction from your favorite problem to SAT, I mean, you first better try to get a good algorithm for SAT than trying to get a good algorithm for your problem. So in that sense, it is like, let's put all our efforts to this problem. So you can also think of that way as, right? In other words, if you don't believe in lower bound x, which is SET-based, then refute SET first before trying to disprove x. Okay? I mean, just the subjective opinion. Okay? But let me tell you what sparsification lemma is. So what's the sparsification lemma? But imagine that you have a reduction which, given a 3 SAT formula phi on n variables and m clauses, produces an equivalent instance of the problem x of size big O of n plus n. So if you started with n variable and m clauses, and you produce this, say, linear reduction. So under ETS, now we will show that there is no size of the instance to the power 1 by 3 algorithm for x. Why? Assume there is such an algorithm A. For a given 3 SAT formula, apply the reduction and use A. Now if you pipeline this algorithm works in to the power little of 1 by 3, then that is to the power little of n plus m 1 by 3, which is to the power little of n. Because m can at most be n cube for 3 SAT. That's the point. If we knew that m equal to order n, if the number of clauses or number was like big O of n, then we get much stronger lower bound that we do not have 2 to the power little of 1 to the power little of size algorithm. Right? So this is where the power of sparsification will come in a minute. Okay, so what is sparsification lemma? Informally, it says that there is a sub-exponential algorithm which reduces the number of clauses of QSAT formula to big O of n for any constant q. Right? Actually, it is slightly different, not different. So for any q greater than or equal to 3, there is a constant that depends on the size of the clause and the epsilon, and it produces basically 2 to the power epsilon n many formulas, where each formula has linear number of clauses, and one is satisfiable if and only if one of these tiny formulas are satisfiable. So given phi nm, I will produce lots of formulas. Each of them has linear number of clauses. Of course, what you mean by linear depends on the epsilon and the size of the clauses. And how many will I produce? Sub-exponentially many of them I produce. So in sub-exponential time, I produce sub-exponentially many formulas so that my big formula is satisfiable if and only if one of my tiny formula is satisfiable. And by tiny, I mean formulas with linear number of clauses. Okay? So what this sparsification lemma tells us, unless ETH fails, there's a constant C greater than 0 such that there is no algorithm for 3-SAT that runs in time to the power Cn plus m. Right? Why? Because proof by contradiction. Assume for every C greater than or equal to 0, if there's an algorithm for 3-SAT in this. That's what we are saying, right? That suppose this is not true, then what will I do? I will set my D appropriately, apply my sparsification lemma, produce a bunch of sparsified instance, solve them with this algorithm, and then disprove or that 3-SAT requires 2 to the power little of n, right? Get a 2 to the power little of n time algorithm for 3-SAT. So that's what this proof does, nothing more. So given this, right, it sets D and epsilon appropriately, applies the sparsification lemma, produces many instances, but sub-exponentially many, but of linear number of clauses, applies the new algorithm, and then it is done. Okay? So it just, again, I have, this slides has all these proofs just for the bookkeeping. You can check for yourself. So this is the corollary we get. Unless ETH fails, there is no 2 to the power little of n plus m time algorithm for 3-SAT. So what else we got? 3-SAT has no 2 to the power little of n algorithm if and only if it does not have 2 to the power little of n plus m, which is nothing but size. So what we'll get now? 3-SAT has no 2 to the power little of n algorithm if and only if it has no size algorithm, if and only if mini 3-SAT is FPT, if and only mini circuit SAT is FPT, blah, blah, blah. So now finally, I have tied them all together now, which basically means that what's the consequence? ETH, if and only if mini 1 is not equal to FPT. So because ETH came, it was easier to use. So in this world, FPT not equal to mini 1 got buried, and rightly so, because I mean they're equal. So why do we care? But this is how two parallel theory built, and they somehow coincided with the sparsification lemma. So for both theory to build, you need a sparsification, right? So that's a single most important discovery in this field, which ties them together. Okay, so if circuit SAT hypothesis fails, then vertex cover has no 2 to the power little of n algorithm because of this sparsification. Okay, so I have like 5 to 7 minutes. So if you have seen how do people show reduction, if you have seen a classical vertex cover reduction from 3-SAT, you make these triangles, and then you just add edges. This is basically undergraduate reduction. Has a vertex cover size n plus 2m, right? So if you just pipeline from normal 3-SAT, so created instance has order n plus m vertices and edges. Now what will you imply? Immediately imply that no such algorithm for vertex cover. You can do this for lots of bunch of problems. I'm not going to tell you. So this is something I wanted to tell you. Okay? So those are like a very standard classroom exercises. If you do this, just trace the n plus m, and you get your lower bounds. Okay? So that's a power of saying the 3-SAT has no 2 to the power little of n algorithm versus it has no 2 to the power little of n plus m algorithm, because now all the reductions that are linear in n plus m gives us the desired lower bound. Okay? So basically, if you wanted to exclude an algorithm with running time 2 to the power little of f of k, and we need to provide a reduction from 3-SAT to b. So if you want to rule out little of k algorithm, then your k has to be like big O of n plus m. If you want to rule out root k kind of algorithm, then you can allow your input to n plus m whole square. So if you look at a lot of reduction for planar instances, they actually blow up to square, and that's perfectly valid because you do have big O of root k kind of algorithm. So this is what you should expect. If you are ruling out k square, then square root of n plus m. If you rule out 2 power little of k, then you need log of n plus m. And if you are 2 power k, you need log of n plus m. So bigger the function you rule out, the difficult your reduction becomes, because power to move around becomes more and more challenging. Okay? But people have done it for different problems. So this is the whole mantra. So like based on what you want to rule out, you have to see what you need your parameters to be in your instances. Okay, so I want to give one reduction for the next 4 or 5 minutes. Okay? And this is for a W1 hard problem. So I want to show that unless ETH fails, there is no f of k n to the power little of k time algorithm for click. Right? So we know that it did not have any FPT algorithm by our assumption, but I'm going to tell you that under ETH we can say, hey, you cannot even improve asymptotically n to the power k algorithm, which basically tries k vertices and checks whether it's a click or not. Okay? So I'm going to give a reduction from 3 coloring. Okay? So what's the 3 coloring? So 3 coloring is you are given a graph G, you want to color the vertices with 3 colors so that every edge is non-monochromatic, or you are not assigning the same color to the endpoints of any edge. Okay? So if you look at a reduction, classroom reduction from 3 SAT, the number of vertices and edges is linear in the number of variables and the clauses. So this is a linear reduction, which implies immediately that you cannot have 2 to the power little o of n plus m algorithm for 3 coloring. Okay? So let's assume that we do not have 2 to the power little of n plus m algorithm for 3 coloring. So this is something which directly follows from the reductions in the class. So unless ETH fails, 3 SAT, 3 coloring does not have such kind of algorithm. Now what do I want to do? So given I want to come up with an instance of click and say, hey, if you had a good algorithm for the click, then I can solve my 3 coloring in 2 to the power little of n plus m. In fact, I will show that I can solve it in 2 to the power little of n, where n is number of vertices. So what I'm going to do, see, so in 3 coloring, we think of them as like we have n variables, but each variable has 3 choices. Now, for the click, we have k variables, the selection of this, but now they can take any of the vertices. So this is like a k variable, but for each variable, we have n possible choices. So intuitively, what I want to do is like choice is here, choice is here. So choices in the left side like 3 power n, because each vertex has 3 possible coloring, and each vertex here has like k variables that we want to select for vertex cover has n. So it's like 3 power n and n power k. Roughly, we would like these 2 numbers to match in our gadgets. Okay? So n is roughly 3 to the power n over k by just this. But how to choose k, we'll decide this later. Okay? Okay? Okay. So suppose this is my graph. Okay? An instance of 3 coloring, and I want to reduce it to an instance of click. So what I do is that I arbitrarily partition my vertex set into groups of size n by k. So how many groups I have? K each, k groups. Now I make a Hughes graph where for every group of this n by k vertices, I enumerate all possible valid partial 3 assignments for this n by k vertices. So how many of them are there? 3 to the power n over k. So for each group of k vertices, right, I'm enumerating all partial valid assignments of these n by k vertices, right? So there is vertices each for each possible partial coloring of this n by k vertices. Okay, so that's the construction. Now how do we give an edge? So now you give if you give an edge between a vertex in this class and a vertex in this class, this represents coloring of some n by k vertices. This vertex represents valid 3 coloring of some other n by k vertices. And I put an edge if I say, hey, together do you give a 3 coloring for these 2 colored classes or these 2 partitions? Then I put an edge, right? So I put an edge between, right? Between 2 of them. If you look at the coloring here, so suppose there's a coloring here, if you notice, here's a coloring blue, red, this. If these are valid coloring, then I put a edge between those 2 partial coloring. So that's the end of the construction. Okay? So left graph admits 3 coloring, if and only if right graph contains a k click. Why? So look at if a graph has a valid k coloring, then you look at the n by k, look at the partial coloring, projection of those n by k vertices. That will be a vertex here. Look at the projection of that coloring to the another group. There will be a vertex here. Now, there's an edge between those two because together they form a 3 coloring of the whole graph. So in particular, they form a valid 3 coloring for the induced subgraph on these 2n by k vertices. And in the reverse direction, if you had a k click in this graph, because these are like bipartite, right? So they will consist of one vertex from each of them, right? So now if you go back, they naturally corresponds to a valid assignment of colors to the vertices. Now it's our job is to check whether they forms a proper 3 coloring or not. If you look at any edge in your graph, if those two vertices belong to the same class, then by definition they have. If they belong to two different class, then how did you put an edge between this vertex and this vertex? Because the corresponding partial coloring were valid for those, and that's end of it. Okay, so that's the equivalence. Now let's look at the running time. So created graph had how many vertices? Capital N. So 3 to the power n by k into k, that many vertices. Let's try k equal to log n. What happens if we set k equal to log n? Then I can show to you that you can rule out 2 power k n to the power little of k algorithms. How? Because if you set k equal to log n, then 2 power k is like n, no problem. What is n to the power little of k? So n is like k 3 to the power n by log n, 3 to the power n by log n, to the power log n. So this is little o of log n because you have little of k algorithm, and you can show this is to be to the power little of n. Okay? Suppose I wanted to rule out 2 to the power k times n to the power big of algorithm. Then you set k equal to log n and do the maths again. So if you wanted to rule out any computable function f of k, then one needs roughly k to choose f inverse of n and then do the maths. But I have no mood to do all this computation at the end of my talk. So this theorem, so unless ET is phase, there's no algorithm for click. So a reduction, we have seen a reduction from click to x, which outputs parameter g of k, then you get corresponding lower bound. So what does it imply? We have seen under ETS, there is no f of k into the power little of k algorithm for independent set, multicolor independent set, and dominating set. Okay? And so what's the take-home message? Set implies ETH, which implies W not equal to FPT, which implies P not equal to NP. So FPT not equal to NP just means no such algorithm, and ETH implies no to the power little of f of k algorithm. Set implies to the power 1 minus epsilon time f of k algorithms are not possible. I haven't talked anything about set except introducing them. You will hear about them much more in the next 2 days. So I'd say that's it. Thank you for your attention.
Questions?
Yes?
So I've noticed that usually when you have a problem parameterized by some parameter k,
Right.
and then you have, let's say, a graph problem, right?
Correct.
And you have a graph on order n, and then when you parameterize by n minus k, one of them is like left one or too hard, and the other one is FPT.
Not always. Like sometimes this phenomena does happen, but it's
a
not.
trend, right? You know.
See, it's not strange. Like sometimes graph problems has lots of combinatorial property. Like for example, I mean, if we know that some, like look at dominating set for example,
Okay.
right? So if a graph has minimum degree 3, I mean, you know that it does not have a dominating set of size, like has size at most say n by 3 or at most n by 2, right? So now if you do n minus k, basically you are parameterizing with the input size.
Yes, so I guess you.
So that answers your questions, right? So for many of these problems, such kind of graph theoretical structural results kicks in. But maybe try, say for example, I mean this I don't know, I'm just making up on my head, is that let's define dominating set, but I want minimum weight dominate. There's a weights on the vertices,
Okay.
and I want dominating set of size k, correct? And of among them minimum weight. What happens if we now try to parameterize by n minus k? I don't know. So is it the numbers? Is it the structure? Is it the graph that's making these problems easy or hard? I have no idea. Yes?
Is there any evidence that W1 is not equals to W2?
We believe so, but I have no idea. Yes?
Why did we encode n in unary again?
Oh, that's a good point. Otherwise, okay. So if you do not encode it, I mean, you don't have to encode it. So one way of looking at it is following. Imagine that if I give you a graph G on n vertices, and now I'm asking you, do you have a vertex cover of size k log n? But I'm only parameterizing by k. That makes sense now, right? It's like I want a solution of a bigger size, but the running time that I'm allowing is much smaller. So you should think of them in that way also. Okay?
It just feels unnatural.
Yeah, it seems unnatural. I have, see, many of these things I have read 2 decades back, and I read them back again after Karthik said me, and I struggle with them for why will someone define such unnatural things. But this padding trick is all over complexity theory, and it makes everything smooth. Otherwise, for example, this is the problem. So I actually thought, why are people doing this? So for example, look at SAT. I thought, look at 3 SAT. So maybe we should be asking that, is there a assignment of weight at most k log n, and I parameterize by k? But then all the theories started to fall apart. So I stopped touching it. It's like, no, maybe there's something more fundamental happening here than I think.
It's time to